My name is Emmanuel Adegoke, and I want to get straight into this project. First of all, I'd like to say my project fulfills the ethical compliance category B2, anonymous football match data. All of the videos I'm going to be using in my project are from Kaggle, and it's completely open for anyone to use. Football data and analytics. What does this actually mean? Data has been described as the new oil by Clive Humby, as we know that data is going to revolutionize the world with its vast amounts. It's been used to create large LLMs, it's going to be used for prediction, analysis, and many more. By large LLMs, we see the rise of ChatGPT needing exorbitant amounts of data. I thought maybe I can combine some of the most favorite things that I like: computer science, data science, and football. Knowing that I've played football for a very long time at a very high level, I thought maybe I could combine the computer science that I'm learning and all these theoretical topics that I'm learning in university and apply that to football. What my project aims to do is to bridge the budget gap in football analysis, because my model and the models I'm going to use are going to be able to detect key points and track players, and thus, as a result, provide cost-effective analysis and provide insights to the audience of coaches, scouts, analysts, or players themselves. What do I mean by the budget gap? In professional football, there is expensive equipment being used because there is a large amount of money and a large amount of budget pool being invested into football. This money goes into things like sensors, and sensors in the football boots, sensors in the football themselves, and high-tech cameras that capture everything by the millisecond. But as a result, lower leagues and football clubs which don't have that amount of money won't be able to afford such things, and thus won't be able to benefit from the useful insights that higher league teams benefit from. And that's the goal of my project, is to provide a way that they can just record matches through a camera and be able to detect players and provide such insights. Thank you for listening to my presentation. We're going to be using a module called Supervision, which is going to be used for things like player tracking, key point detection, ball detection, and it's imported from RoboFlow. So this is just a single frame. I'm going to explain how my code works. So let me explain how things work. We use a model to crop each player, to detect players and crop them using non-maximum suppression to find the best bounding box to crop the player. Additionally, we use SIGLIP for feature extraction, which generates 1 by 768 embeddings, which are invariant changes in pose, lighting, and camera angles, perfect for the dynamic nature of football footage. Alternatively, we could have used ResNet or other models, but I'd say SIGLIP is much more tailored to this task, offering better efficiency and robustness. We then use UMAP for dimensionality reduction, which reduces these vectors to just 3 dimensions, preserving spatial relationships between the data points, making it ideal for visualization and clustering. Alternatively, we could have used PCA, but it loses a lot more of the data's underlying structure, like how the players' features relate to each other. Or additionally, we could have used TSNE, which is quite effective, but it's much more computationally heavy, because let's say, for example, its computational complexity is around ON squared, while UMAP is ON log n, which is much more practical for my data set. This helps reduce the computational overhead and improves processing time. We then use k-means for clustering. Why? Because we just know that k equals 2. We don't need to know much more, because I know that k is going to be 2 for all. We can assume that k equals 2 for all football matches because there's only 2 teams. We could have used hierarchical clustering, but it's really slow, and dbScan as well, but it can falter with uneven data distributions. It might detect that there's less players than others and all the other stuff. So I'd say K-means is probably the best method for now. I'll always look to maybe improve on this by using maybe a different clustering technique, or instead of SIGLIP, I'll use something else, or instead of UMAP, I use something else. But for now, I found that these best three work great in unison. Basically, this diagram illustrates how a homography transformation is used to convert a video frame from the camera into a standardized pitch view. The video frame on the left represents a raw image captured by a camera, showcasing a single perspective view on the pitch, and it's also indicated by here. So the standardized pitch view on the right is the result of the homography transformation. It provides a top-down bird's eye view of the pitch, making it easier to analyze a player's position and movements. A transformed point in the view is represented by these coordinates x prime, y prime. The homography transformation itself is represented by this equation here. This equation is a 3x3 matrix H, which is used to transform these original coordinates x, y from the camera's video frame into these standardized coordinates x prime, y prime. Okay, so let's just get started with the showcase. How this works is basically, because I'm using Google Colabs, I want this to be as customizable as possible. By defining this, we can have the option to show many things, such as showing the stats, showing an expected threat grid, showing the players, but obviously you want to show the players, of course. Show the heat map. The heat map implementation isn't working yet. And display the graph at the end, show FPS, and predict the ball movement, which is also not working yet, which is something I do plan to implement and use something like a Kalman filler to implement. So let's say we want to show the stats. We want to not show the XT grid. We want to not show the heat map. And we want the clip duration to be roughly 5 seconds. And if we do this, we run this, which basically goes through using the annotators, using the trackers, getting all the values, checking if some widget values are true or not. And if so, it changes how it outputs this whole code block. So let's see an example. I've fully processed everything. As we can see in the log files, we can see that there's a logs file if the ball is being detected, if for each number of players detected and each number of players tracked. We must detect the distance from the ball to each player. It says meters here. It's not really meters. It's more an arbitrary thing. We see that the possession history has been for team 1 and the recent possession has been for team 1. We know that team 1 basically has only the possession of the ball, and yeah, I mean, it's just being confirmed right here and then. As I say, here is the final output. You can see the FPS and the stats. We can see the homography transformation. We see that the ball is being tracked with a triangle annotator. As this is only 5 seconds, we don't really know the full context of the clip. Each clip is only 30 seconds. And imagine how things would look like over a longer span. Let me show you a quick overview of the code. This update possession function is being called each time there's a frame that's being processed. We get a minimum distance. The minimum distance from, it's not really in meters, for a player to be considered in possession. And we have a smoothing factor, so there's not really much of a constant change in possession. Let's say there's like a little scramble for the ball. I just make sure to keep that in mind. We calculate the distance between the ball and each detected player using the Euclidean distance between the ball and the player. And maybe I could have used something else, but I thought maybe let's just keep it simple. We can use Euclidean distance. I've tried Manhattan distance. It was just kind of a bit weird. So we just keep it as Euclidean distance for now. If there are any valid distances, we determine the closest player and we determine their team. I use CVAT to create bounding boxes, and I use that to compare it to the model. Here are some of the outputs. I also did the same for class-specific outputs. Here are the metrics which talk about the system performance and object detection at an IOU above 0.5. As we can see, here's the average processing time. I'm going to try and aim to reduce that to at least under 3 seconds or less if possible. Here are the class-specific metrics. As you can tell, with an IOU of 0.5 or above, the ball model prediction struggles really hard. This is something I aim to improve to at least get it to a decently high record or score for each category.